Okay, so this part of the lecture we will discuss about bifurcations. I mean, what is a bifurcation? I hope in all of your capstone projects you might have heard about the word bifurcations at least once. Okay, so what is a bifurcation? So that's what we'll be covering in this lecture. What are bifurcations in simple systems? Okay, what are bifurcations in simple systems? And then we will simple system in the sense one dimensional systems. So for one dimensional map, we will find what is a bifurcation. Okay, different kinds of bifurcations are present in one dimensional map. We will see that. And we'll also see that this can also be present in higher dimensions. Like in two-dimensional maps also, you will see these kind of bifurcations. In three-dimensional maps also, you will see similar kind of bifurcations. But also, higher dimensions will lead to new novel bifurcations. Higher dimensions can give you novel bifurcations as well. Okay, so in 2023 I found out a new bifurcation, okay, which was not yet covered since 2008 or 11. Okay, so that's how the higher dimension can give you different geometries and hence can lead to new bifurcations. But since this class is for basic nonlinear dynamics, we'll cover the basic bifurcations or simplest bifurcations. Okay, so let me give you a simple idea of a bifurcation. Okay, so the simple idea is like this. This is your ground. Okay, and this is your metal rod. Suppose this is a metal, right? This is a metal rod, and what you do is you place an iron block here, right? You place an iron block here. What will happen? Like it will withstand some weight. Suppose this is 5 kg weight. It is withstanding this 5 kg weight, right? Now what you do is increase a bit of more mass to it. You increase a bit of more mass, okay? I mean more mass, so bigger, like maybe say 10 kg. Then what will happen is the metal rod will start to buckle. Okay, how it will start to buckle? Maybe it will be something like this, right? It will take a swift state. Increase it more, say 20 kg, the block. Increase 20 kg. Okay, what will happen? It will break. It will break. Like it will reach a what do you call that? A critical point after which if you put any mass, it will break. The metal stripe in between will break. That breaking point is known as a bifurcation. I mean the point or the weight at which the block, at which the stripe breaks. Weight at which the stripe breaks is known as the bifurcation point. And the weight at which it breaks, the special weight at which it broke is referred to as the bifurcation parameter. I mean at that parameter, the bifurcation happened. Okay. So at what weight the metal stripe broke down. So that is the bifurcation parameter at which it happened. Okay, that is the bifurcation point. What is the bifurcation point? Parameter at which the metal stripe broke. Okay, fine. And the metal stripe breaking when you increase the weight is referred to, the process is referred to as bifurcation. So let us see. I hope you have already seen bifurcations in different systems. One of the examples is like, I hope you have seen something like this. Okay, fixed point, and it is going to period 2 orbit. I hope you have seen this, right? It is known as a period doubling bifurcation. So what is the bifurcation point here? So you remember in a logistic map what you had, this is the logistic map you had, xn plus 1 is mu, xn into 1 minus xn, and you varied mu here on the x, and this is x and you varied mu here. So this is the stable fixed point. Okay, this is the stable fixed point. And what happens is at this point, it bifurcated into a period 2 orbit. So this is the mu star, mu PD. This is the special parameter point at which the bifurcation happened. That means the structural, what you call the structural way of this state changed. The dynamical state changed from a fixed point to an oscillatory state. Fixed point is a rest state. What is a fixed point? This is a fixed point. I mean, we are at rest. We are not changing. Whatever you do, I will be here. Okay. If you hit me also, I'll be here. Okay. Hopefully. But when you increase the parameter a bit more, how you increase the parameter a bit more? You suppose you had gym and all this and you built very big muscles, okay, and you come and hit me, then I will, it will disturb me, right? Then what I will do, I'll be doing like this, right? I'll be doing like this. So it will be oscillatory mode, right? Oscillatory mode. So you can see this is the oscillatory mode, like it is transferring between the two periodic orbits, period 2 orbit, right? How this orbit look like? If you take the time series of this fixed point, how it will look like? Constant line. This is the time series n, right, for a fixed point. How it will look for a period 2 point? Point A, point, say point B. Again, the same thing will happen. Point A, point B, point A, point B, point A, point B, right? So it's a periodic orbit time series, right? Period 2 orbit. So this is a bifurcation, right? So this lecture will be about to studying these kind of simple bifurcation in 1D maps. These kind of simple bifurcation in 1D maps, okay? So we will see this, right? So when a bifurcation occurs, actually, that's one of the basic things to ask. To be honest, this kind of bifurcation occurs depending on the dimension of the map, okay? So suppose you have a 1D map. For a 1D map, you have the map as xn plus 1 is equal to f of xn. And there is a parameter say mu. There is a parameter say mu. We know that as we vary the parameter mu, the state of the system changes. That is, one point goes to next point and keeps on evolving. That's a dynamical system, how it evolves. Right? Fine, okay. So now when a bifurcation happens, so a fixed point, I mean like a fixed point, say fixed point, I'll denote it by x star. You know what is a fixed point? What is a fixed point? It stays same. So x star is equal to f of x star. That is a fixed point. So a fixed point x star, right? A fixed point x star that satisfies x star equals to f of x star, right? Fine. Undergoes a bifurcation. Undergoes a bifurcation when the derivative, the absolute value of the derivative at the fixed point crosses 1. Okay. When the absolute value of the derivative crosses 1, right? In one-dimensional maps. In one-dimensional maps. Because in one-dimensional map, you have nothing but derivative. Okay. But when you consider a two-dimensional map, you have x and y, you will have a Jacobian matrix. Okay. Like a 2 by 2 matrix. Then in those 2 by 2 matrix, you will compute the Jacobian at the fixed point. That means the eigenvalues at the fixed point. And those eigenvalues will determine the stability. That means that this condition will have another condition, that is all eigenvalues are less than 1 for your stability. Okay, the moment they cross 1 eigenvalues, a bifurcation happens. Okay, but remember here the modulus of the derivative for 1D maps. For 1D maps, you only need the derivative, no eigenvalue will be there. But in higher dimensional maps, when you go, you will have a matrix, right? And therefore the concept of eigenvalue comes, and the eigenvalue play a critical role in deciding the bifurcation, right? Got the idea? So, but today's class is all about 1D maps and their bifurcation. So we'll play around with the derivative. We'll play around with the derivative. So this is the definition of the bifurcation. A one-dimensional map, xn plus 1 is equal to f of xn, undergoes a bifurcation. A fixed point undergoes a bifurcation when the derivative of the fixed point absolute value crosses 1. Okay, crosses 1. The moment it crosses 1, there is a bifurcation. Okay. If it doesn't cross 1, there will be no bifurcation. We'll see this in action. Okay, we'll see this in action. Let us consider one example. Okay, let us consider one example. Different bifurcations we'll consider here. The first and famous bifurcation is known as the saddle node bifurcation. Saddle node bifurcation. So for each bifurcation, we will take an example of a 1D map and show what do I mean by this bifurcation. Okay. So saddle node bifurcation. So let us consider, let's consider 1D map of the form xn plus 1 is equals to mu plus xn minus xn square. Okay, this is f of xn. F of xn and the parameter is mu. I hope it is okay. Right? This is a 1D map. Is okay with everyone? Now, suppose mu is greater than 0. If mu is greater than 0, then there are two fixed points. Then there are two fixed points. Right? If mu is greater than 0, are there two fixed points? Agree with me? Okay. So how many fixed points are there? There are two fixed points. Why? How we can know? Can you find this x star equals to f of x star? So what you get? X star equals to mu plus x star minus x star square. I don't know how this happened. Anyway. Okay. X star equals to mu plus x star minus x star square. So what you get? Mu minus x star square is equal to 0. So x star equals to plus minus root mu. Right? So there are two fixed points. One is x1 star is equal to plus root mu. X2 star is equal to minus root mu. Now what happens with that? Now what happens with that? Now remember that which one is stable and unstable? I told you in previous classes when it is stable, when the derivative is less than 1. Okay. So can we compute the absolute value of the derivative at x1 star and x2 star? Now what is the derivative? Can you tell? The f prime of x is equal to 1 minus 2x. F derivative here is 1 minus 2xn, right? From this, right? So what is the derivative from this? Is modulus of 1 minus 2xn star. 2x1 star. What is it? 1 minus 2 root mu. So when it is stable, this should be less than 1. Is this less than 1? Is this less than 1? 1 minus something you are doing. Of course it will be less than 1. So it is stable always. It is always stable. So stable. Right? Good. Now can we go to the next fixed point x2 star? So similarly 1 minus 2x2 star, right? So what it will be? 1 plus 2 root mu. This is always greater than 1. Always. Always greater than 1. So always unstable. Isn't it? Is it clear? Since the derivative is greater than 1, always, irrespective of mu, it is always unstable, right? But one thing you notice that if mu greater than 0 only, there are two fixed points. If mu less than 0, what happens? If mu less than 0, what happens? For mu greater than 0, what is the story so far? We have two fixed points, x1 star, x2 star, right? x1 star is always stable, x2 star is always unstable. For mu greater than 0. Now what happens for mu less than 0? Yes, so fixed point is always real. So no fixed point. No fixed points. Because you have a root over sign. Right? So therefore x1 and x2 star will be complex, which doesn't define a fixed point. So therefore there is no fixed point. Right? Okay. Now notice that when mu tends to 0, what happens? When mu tends to 0, what happens? When mu tends to 0, x1 star, fixed points x1 star and x2 star comes closer to each other, isn't it? Comes closer to each other. You can think of this as a number line. You can think of it as 0. x1 star, x2 star is here, x1 star is here. This is plus root mu, this is minus root mu, right? When mu goes to 0, what happens? This fixed point goes to 0 and this fixed point goes to 0, right? They approach each other. And we know, and we have a condition that if we are using stability, I mean the fixed point is stable, then it is a stable like this. If it is stable, x2 star is unstable, so I will use a red one. For stability, I will use blue. For unstable, I will use red. That's my color pattern. Okay. For stable, I will use blue. For unstable, I will use red. Okay. Fine. So you can see this is the unstable one, and this is the stable one, right? This is the stable one, right? So what is happening? When they come closer to each other, they will collide. At mu, when they collide, at mu equal to 0, right? The fixed points x1 star and x2 star collide at mu equal to 0. Fixed points x1 star and x2 star collide at mu equal to 0, right? And afterwards what happened? They annihilate. Stable and unstable, they collide and annihilate. So therefore, for mu less than 0, there is no fixed points. So if I want to capitulate everything in a table, I will do like this. Okay. So the idea is like, this is the mu. So for mu greater than 0, there is x1 star and x2 star fixed points. x1 star is stable, x2 star is unstable, right? Fine. Now when mu equal to 0 happened, x1 star and x2 star collided. The stable and unstable fixed point collide, and that is a bifurcation. That is a saddle node bifurcation. Okay. So that is the saddle node bifurcation. Fine. And after that, what are the cases remaining? Mu less than 0. After collision, they annihilated each other. Stable and unstable collided, annihilated each other. So they got destroyed each other. So therefore, for mu less than 0, no fixed points are there. So I hope you understood that how a saddle node bifurcation works. So for mu greater than 0, so how it happens? So when mu was positive, there were two fixed points, stable, unstable, right? When you decreased mu value from positive towards 0, the fixed point appeared close to each other. At mu equal to 0, they collided, stable and unstable collided, so they got destroyed. After that, mu less than 0, no fixed point is there. That is the behavior of saddle node bifurcation. I hope this intuition is quite clear, right? So you are not able to visualize this much, but you will visualize it when we go to 2D systems. You will see an animation how the fixed points come closer to each other and annihilate. Okay, but see, this is 1D system, so you are not able to see that. Okay, just a one variable x. So, but why you have to believe me? That's the question. You told me, you should tell me that, sir, you told below point that a fixed point x star undergoes a bifurcation when the derivative process 1. Here you never discussed anything about the derivative. You just told they collide, they annihilate, and that's a saddle node bifurcation. How we will believe actually it is a bifurcation or not? So if it is a bifurcation, the derivative should pass through 1. The modulus or the absolute value of the derivative should pass through 1, right? So when I told when there will be a bifurcation at mu equals to 0. So at mu equals to 0, the derivative should cross 1, right? So can we compute the value of the derivative at mu equal to 0? So at the bifurcation point, at saddle node bifurcation point, at the saddle node bifurcation point, that is mu equals to 0, the derivative of this one is what? Can you tell me? It is 1 minus 2, any value you take. So whatever, irrespective of the fixed point, it will be 0 multiplied by 0. So it is 1. So it is crossing 1. It is crossing 1. So at that point, at mu equal to 0, you have the derivative equal to 1, the absolute value of the derivative. So therefore, a bifurcation happens. Bifurcation occurs as we had discussed, right? Is that okay? Hmm? So now you know that the two fixed point, one stable, unstable, when they come closer and collide, it is a special phenomenon, right? Because at that point, the derivative is equal to 1, okay? And that is a bifurcation. Because after that happens, there is no fixed point. So why we call it a bifurcation? Because there were two fixed points, and as you vary parameter, they come closer and annihilate. And after that, there is no fixed point. So you went from a state of two fixed points to zero fixed points. So there is a qualitative change in the dynamics of the system, which is referred to as a bifurcation, right? Is there a qualitative change happened? Why a qualitative change happened? From two fixed points, you went to zero fixed points. So your system behavior has changed, right? Your system behavior changed. So therefore, it is a bifurcation, right? I hope it will be more clear if I can show you the Python code for this. So let us see the Python code for this. Maybe here. Yes, you can see this guy, like the same function which I have given you, the same function I am taking over here. Okay, you can see this phenomena happening right now. Okay, the blue color, so the y-axis is the fixed point, you can see. The y-axis are the fixed points. The x-axis represents the parameter, right? So what you are seeing here, you are seeing that for mu greater than 0, somewhere here you see two fixed points there, right? Now when mu comes closer to 0 on this side towards left, the fixed points appear close to each other and they collide and annihilate at this point, right? So therefore, this is an example of a saddle node bifurcation, right? I hope that is clear. No? Shall we go back to the next one? Okay. Now let us come to something very interesting. Okay. Transcritical bifurcation. I hope you can see it in real life. Okay. I hope you know about this, right? Like if you throw, like on Diwali, maybe on Diwali, one person throws a bomb here, another person throws a bomb there. Okay. What happens? They collide and annihilate, right? No bomb remains. Okay. They blast each other, right? Isn't it? So that's a kind of real example of a sudden bifurcation. Right? So yeah. Or maybe I can give you an example that when you have a red stove, like red hot iron, and you put ice on it, they annihilate each other. Right? So that's how it is. Okay. So let us come to something very interesting that is known as a transcritical bifurcation. Okay. Transcritical bifurcation. What is a transcritical bifurcation? Transcritical bifurcation means exchange of stabilities. In this kind of bifurcation, exchange of stabilities will be happen. So I will tell you the joke first, and then we will see the mathematical behavior that you see the same example. So let us take person A and let us take person B. Okay, person A, person B. So what happens? Person A suffers from cold. Okay, so what happens? He sits with person B, and after that, person B catches the cold, and person A recovers from the cold. Right? Have you seen this phenomenon happening? Yes. So what happens? So person A was stable. No, sorry, person B was stable before. Person A was unstable. When they sat together, like close to each other, what happens? Person B started to take the cold, and person A recovered. Right. So you saw exchange of stability took place. Right. So same thing we will see here. Right. Exchange of stability will take place. So this is just an example. Don't. Okay. So let us take this example. xn plus 1 is equal to 1 plus mu xn minus xn square. Where you see this behavior? I mean, the behavior of person A, person B, I told you right now. You see this in this example, right? So take this example, 1D map, xn plus 1 is 1 plus mu xn minus xn square. Okay. So first of all, before doing anything, you compute fixed point of a system because they are the simplest invariant sets of a discrete map, right? They're the simplest invariant sets of a discrete map. After that comes periodic orbits, quasi-periodic orbits, chaotic orbits, many other things. But the simplest one is a fixed point. So this system, the question now is this system has how many fixed points? So fixed point x star satisfies x star equals to 1 plus mu x star minus x star square, right? So can you tell me what you get? So you see x star will cancel. So you will have mu x star minus x star square equals to 0, right? So if you take it, x star is mu minus x star equals to 0. So you will have two roots, right? One is x1 star equals to 0 and another is x2 star equals to mu, right? If I'm okay with this, fine. I hope you got this, no? Now for mu less than 0, for mu less than 0, we will analyze. Okay, for two cases we will analyze. For mu less than 0 and for mu greater than 0. Okay, for mu less than 0, which fixed point is stable and which fixed point is unstable? That is our task. Okay, understood the task. So for mu less than 0, for mu less, sorry, that's what we need, right? Okay, good. But it got stuck. Okay, let us see. For mu less than 0, what happens? Like, in order to compute the stability of fixed point, what you have to do? What you have to do? Compute the derivative, right? So what is the derivative? Not the derivative, but the absolute value of derivative at the fixed point. So what is the derivative here? Can you compute the derivative of the fixed point? 1 plus mu minus 2x star. Okay. So we will have x1 for first fixed point. That is, what is for the first fixed point, x1 star is equal to 1 plus mu minus 2x1 star. So what is x1 star? 0, right? And this will always be greater than 1. 1 plus mu will always be greater than 1, right? So x1 star is unstable, right? Now coming to the second fixed point, f prime at x2 star, right? So what is x2 star? X2 star is mu. So that will be 1 plus mu minus 2 times mu. What is this guy? 1 minus mu. So this will always be less than 1. This will always be less than 1, right? Isn't it? So if it is always less than 1, so x2 star is stable. Okay, so what we got here, can we write it? So for mu less than 0, x2 star is stable and x1 star is unstable. So I am writing the red as unstable, blue as stable, right? Now can we do the same thing for mu greater than 0? Now for mu greater than 0, the same derivative, right? The same derivative won't change. I mean, the derivative will still be 1 plus mu minus 2x star. Okay. So first is the derivative at x1 star. So it will be 1 plus mu minus, yes? Any ideas? I think I did something wrong, isn't it? Are you seeing where I did something wrong? I mean, this is why I tell, don't always believe me. Where I did wrong. Where did I did do wrong? Anyone who will tell? Yes, since mu is less than 0, 1 plus mu will be less than 1, not greater than 1, right? So therefore, this is wrong, right? So it will be less than 1, right? So, and when you have x2 star, 1 minus mu will in turn be greater than 1, right? So this guy will be greater than 1, right? So what is the mistake here? So you can eliminate, so these things, right? So what you got? Yes, fine. Okay. So what we will write here now? X1 star is stable, x2 star is unstable, right? Okay, got the idea? Now can we do for mu greater than 0? For mu greater than 0, what you have? For mu greater than 0, what is x1 star? 0. So this will be 1 plus mu, and this is always greater than 1, right? Yes. So it is unstable. So x1 star is unstable. Now second case, when you take the derivative at x2 star, right? So what you get? 1 plus mu minus 2 times mu. So this will be 1 minus mu, right? Since mu is greater than 0, this will always be less than 1, right? Since mu is always greater than 0, 1 minus mu will be less than 1. You are taking some positive quantity from 1, so it should be less than 1. That's my idea, right? So x2 star will be stable. So for mu greater than 0, what is the story we have? For mu greater than 0, we have x2 star is stable and x1 star is unstable. Now, do you see something happening here? Now, can you analyze the scenario here? Yes. Before, for mu less than 0, the fixed point x1 star was stable and x2 star was unstable. The moment I changed mu to be positive, they exchanged their stabilities. That means x1 star became unstable and x2 star became stable. So you can see during this transition, exchange of stability took place. Exchange of stability took place. Isn't it? Exchange of stability has taken place. So this is a kind of a bifurcation, right? This is a kind of a bifurcation. But is it a bifurcation? Now to know about this bifurcation, so you can see the moment it passes mu equal to 0, then this exchange is happening. I mean less than 0 one case, greater than 0 one case. So in between, you have mu equal to 0, right? So what is the value of the derivative at mu equal to 0? If it is a bifurcation, it should pass through 1, right? So does it pass through 1? That's the question. So you have to compute the value of the derivative at mu equal to 0. At mu equal to 0, right? So what you get at mu equal to 0, it is at mu equal to 0, it is 1 plus. So value of the derivative is this, right? So it irrespective of x star and mu equal to 0, you will always have it 1. Because you take two cases. When you take x1 star, it is 0 and it is 1. Even if you take x2 star, at mu equal to 0, it is still 0 and it is 1. Right? So the derivative crosses 1. So the derivative crosses 1. This implies a bifurcation takes place. A bifurcation takes place at mu equal to 0. And since exchange of stability has taken place when mu equal to 0, this is known as a transcritical bifurcation. This is a transcritical bifurcation. Okay, fine. Ready? Shall we see this transcritical bifurcation again in Python? Okay, we'll see this in Python working. Okay, so we'll see, try to see this. So the same function I am taking, what I have shown you. Okay. And what I'm trying to do here, you can see here is this case. For mu less than 0, observe the x-axis here, observe the cursor here. For mu less than 0, you have a blue and a magenta line. Okay. Blue is the stable x equal to 0 and the magenta is unstable x equal to mu. Right? Two fixed points are present. Agree? Why this looks like this? Why the figure looks like this? Can you break it down within some seconds? I mean, you should be sharp like this. Then only things you can visualize. One thing is one fixed point is 0, right? If fixed point is 0, what will happen? It will always lie here, the blue point. Another fixed point is mu, right? So it will be like y equal to x curve because you are plotting x versus mu, right? So it will be just like y equal to x line, right? Now for x, for mu less than 0, some phenomena happens. For mu greater than 0, another phenomena happens, right? For mu less than 0, can you tell me which is stable, which is unstable, seeing your notebook? For mu less than 0, don't tell x1, tell 0 and mu. Then it will, you can easily visualize this. 0 is stable. So therefore I have plotted it in blue. What is unstable? Mu is unstable. So it is lying here, dotted lines, right? Magenta, right? You see, they come closer, they collide here. They come closer, they collide here, they exchange their stability. Okay, like person A, person B close, they exchange their stability. Okay, so after exchanging their stability, what happens? For mu greater than 0, which is stable for mu greater than 0? X2, no, mu. So mu you can see green. So you can see in the legend that is stable x equal to mu. And this orange line is x equal to 0, which is unstable right now. So can you see the stable one, the fixed point 0, which was stable here for mu less than 0, is now unstable. And the fixed point which was unstable here for mu less than 0 is now stable here on the mu greater than 0. So now you can see an exchange of stability has taken place. And mu equal to 0, the derivative crosses 1. So therefore it is a bifurcation. And since this is a new kind of bifurcation as studied before, that is a saddle node, where exchange of stability take place, this is known as a transcritical bifurcation, right? A new name. In saddle node bifurcation, what happened? They come closer, collide, annihilate, destroyed. No other fixed point there. But here they come closer, collide, but exchange their stability and go back, right? Is it understood? Your group is understood, right? Okay. I hope it is clear. Yes. So let us now look into another example. Okay, another kind of bifurcation. Okay, which is kind of your assignment. It will be an assignment. I mean, after I explain, it will be an assignment for you. Okay, there is a question. So it is known as a pitchfork bifurcation. Pitchfork bifurcation. What is a pitchfork? Pitchfork, do you know? I hope everyone might have seen this. Okay. Yeah, I think everyone has seen this in every part. I think, yeah. So this is something well known to the community. So you can, this is a pitchfork. Okay, this is a pitchfork. You will see how a mathematical system exhibit a phenomena like this. Okay. So let us see. This kind of bifurcation happens with symmetric systems. This kind of bifurcation happens with symmetric systems. What do I mean by symmetric system? So I'll give an example. Let us consider this. For every bifurcation, we are taking a new map. Okay. At the end, I will tell you why. Okay. At the end, I will tell you why we have taken new map for each of them. Okay. So let us consider this map. This is a 1D map. Okay. Now this is an odd function, right? The right hand side is an odd function. If you put x to minus x, so this is like f of xn, right? So if I tell f of minus xn is equal to minus of xn. Is it true? Is it true? Yes, because xn is an odd function, xn cube is also an odd function. The minus sign will just penetrate, okay, and come out of your sign, right? So therefore, it's an odd function, right? So therefore, this is a symmetric system. Symmetric system. And you usually see this bifurcation in symmetric systems. Note that maybe you have a question, sir, you have considered two other maps before. Why in those maps you don't see pitch? Let us go. You can see it is x1 square is there. Xn square is there. So it is not symmetric. F of xn is f of minus xn is not minus of f of xn, right? So it is not symmetric. Similarly, you go here. It is also not symmetric because xn square is there. But this map is something new. You have a cube. So therefore, an odd function. So therefore, it is symmetric. And usually in this kind of symmetric system, you see pitch for bifurcation. Okay. You see a pitch for bifurcation. Fine. So let us see the same analysis. The story is the same. You have to compute fixed points for mu less than 0, mu greater than 0, and see where a bifurcation is happening and whether some stability changes are happening. If it happens and new feature happens, it's a bifurcation. Right? Got it. Okay. Let us consider mu less than 0, the scenario of mu less than 0. So for when mu less than 0, what happens? How many fixed points are there? That's my question. How many fixed points? So x star satisfies x star equals to 1 plus mu x star minus x star cube, right? Okay, agree. So you can see x star cancels with this 1 times x star and you are remaining with mu x star minus x star cube equal to 0. So x star times mu minus x star square equals to 0, right? So you will have x star equals to 0 and x star, x1 star, x2 star is plus root mu, x3 star is minus root mu. Am I clear? I hope it is clear. Is it clear with the calculations? Simple calculations, right? Now for mu less than 0, how many fixed points are there? For mu less than 0, how many fixed points are there? Yes, for mu less than 0, how many fixed points are there? Yeah. No, see very carefully. There is a root over sign. If there is a root over sign and you are taking a negative quantity, what it makes? Complex number. Can a fixed point be a complex number? No, fixed points are real numbers. So therefore, there can be only one fixed point. So this and this are eliminated. Only one fixed point, that is x1 star equal to 0, remains. So for mu less than 0, only one fixed point exists. Only one fixed point, that is x star equals to x1 star equal to 0 exists. Right? Fine. And the fixed point which is existing, is it stable or unstable? That is a question. Fixed point that is existing, is it stable? Now the next question is x1 star stable? What do you think? To answer that, what you have to do? Compute the mod, no, not derivative. Absolute value of derivative. Absolute value, be very careful. Absolute value of derivative. So what is the absolute value of derivative at x1 star fixed point? So what is the derivative of the map, first of all? Can you tell me? It will be 1 plus mu minus, right? So what is x1 star? 0. x1 star is 0. So what you will have? 1 plus mu. And mu is less than 0. So 1 plus mu will be, mu is less than 0. If mu is less than 0, 1 plus mu should be, if mu is less than 0, modulus of 1 plus mu should be greater than 1 or less than 1? Less than 1. Is it? Sure. 1 plus mu is less than 1. If 1 plus mu is less than 1, the fixed point is stable. Yes. So it is stable. So when mu is less than 0, let me write the story here, story so far. For mu less than 0, only one fixed point, x1 star equal to 0, and that is also stable. Okay, that is the output we did here. Now what happens? What happens for mu greater than 0? What happens for mu greater than 0? For mu greater than 0, how many fixed points are there? Who will tell? Yeah, how many fixed points are there? 3 fixed points. Yes, you should be confident. So there are 3 fixed points. What are the 3 fixed points? x1 star, x2 star, x3 star. Now we have to analyze which one is stable and unstable. Right? Right? So can we find modulus of x1 star? That is, can you tell? 1 plus mu? Yes, minus 3 x1 star. So what is x1 star? 0. So it will always be 1 plus mu, right? Now mu is greater than 0. If mu is greater than 0, what is 1 plus mu? Greater than 1, right? So if it is greater than 1, what is it? Unstable, right? Okay. Now let us go to the next fixed point, x2 star. So it is 1 plus mu minus 3x2 star, right? So what is it? x2 is root mu, right? x2 is plus root mu. So x2 star square will be 3 mu, right? So 1 minus 2 mu, right? Still greater than 1. No? Less than 1. So it is stable. Now modulus of x3 star. The new fixed point, another fixed point. 1 plus mu minus 3x3 star square, right? What is it? 1 plus mu minus 3 mu, same. 1 minus 2 mu. Since mu is greater than 0, 1 minus 2 mu should be less than 1. Again stable. So what is the story from this? Another story is, new story is, for mu greater than 0, the fixed points x2 star equals to plus root mu and x3 star is equal to minus root mu are stable, and x1 star equal to 0 is unstable. Can you see something happening here? No, because there is a square. There is a square. So plus mu minus mu doesn't matter. Same quantity you will get when you square, right? So can you see something is happening here? What is happening here? So let me draw the stability diagram for you to understand. Okay, let us use the colors. So this is the plot you will see in Python also when you code it up. So this is our x star, that is the fixed point on the y-axis. So y-axis is fixed point and x-axis is the parameter mu, right? Now this is 0. Now this is 0, right? So what happens here? For mu less than 0, for mu, suppose this is 0, this is the line 0 here, point 0. For mu less than 0, you are seeing the 0 fixed point, which is stable, right? You are seeing a 0 fixed point, which is stable, right? Now what happened to that fixed point when mu greater than 0? Unstable. So I will put red lines, red dotted lines. Is it okay with everyone? 0 dynamics. Now let us come back. Now for mu less than 0, do fixed point x2 star and x3 star exist? No, because it is already written here. They don't exist. For mu less than 0, they don't exist. Now for mu greater than 0, they exist. Now for mu greater than 0, both of them exist and are stable. Okay, but yes, but they are root mu. So it will follow a parabolic shape. It is like root mu. So it will follow like a parabolic shape, right? Agree? So how it will look like? Both of them are stable. So I will put parabolic shape. And one is positive mu, root mu. So it is lying above 0. And one will be symmetric and below 0 because they are negative, right? So since they are negative mu, it will go like this. Can you see the pitchfork now? Can you see the pitchfork which I drew before starting of the bifurcation? So this is the shape of a pitchfork. This is the shape of a pitchfork. So therefore, they named this bifurcation as pitchfork bifurcation. Okay. Now, why do you believe me? Is it a bifurcation? You have to check the derivative at mu equal to 0. So at mu equal to 0, this is the last line. Mu equal to 0, what is the value of the derivative? Can you tell 1 plus mu? At mu equal to 0, all are 0. So minus 2x star, and this will be mu is 0, x star is also 0. So they are 1. Why? Because mu equals to 0 and x stars will also be 0 because mu equal to 0. Right? Because mu equal to 0 means this will go to 0, this will also go to 0, and this is also 0. So all three fixed point converge to there at mu equal to 0. All three fixed point appear here. All three fixed point appear here at 0. At one point. So therefore the derivative is 1, a bifurcation happens. Agree? Agree? Now let us see this in Python. Okay. So you can see this is the same plot I have done, the same example you are seeing right now here. So you can see for mu less than 1, the fixed point is only one fixed point at 0 is there at origin. You can see this origin here. Only one fixed point is there for mu less than 0, for mu less than 0, right? And when you cross mu greater than 0, this fixed point became unstable and two symmetric parabolic kind of fixed points are there which are stable. Agree? Fine. But this was not the case in transcritical bifurcation, remember. Therefore, I overlapped this. In transcritical bifurcation, you were seeing linear functions. I will remind you again, transcritical bifurcation, how it looked. All were linear. But in pitchfork bifurcation, they are symmetric parabolic, right? Understood so far? Now, another task is there. Okay, your task is second task. This is the first task. Okay, second task is you have to find about period doubling bifurcation. Period doubling bifurcation for this map. So your assignment is compute period doubling bifurcation for xn plus 1 is equal to mu plus xn minus xn squared. Okay, fine. You have to do the same exact steps as I have done, and I will ask someone to come to the board and do it randomly, right? Agree? That sounds like a good idea. So shall I move to the Python code? Yes, Python code. So this is the Python code for that function, and you can see, yes, exactly at mu equals to 1, you are seeing a period doubling bifurcation. So the fixed point is there, the fixed point was there, and suddenly it doubled. And this point is known as the bifurcation point. So you will find that at mu equal to 1, when you do the calculations, at mu equal to 1, you have a period doubling bifurcation, right? And later to the class, we will compute Lyapunov exponents, right? So on the side, you can see Lyapunov exponent diagram, right? And at this point, when the bifurcation occurs, a Lyapunov exponent touches 0, right? This is a very important idea, okay? Normally, many people don't know about this. So whenever you have a bifurcation, the Lyapunov exponent will kink at 0. So this point you see here, it is kinking. Another period doubling bifurcation is there. Another point it is kinking, another period doubling bifurcation of this. So whenever it is touching 0, whenever a Lyapunov exponent is touching 0, a bifurcation is signaled. This we will learn in after many classes. Okay. So I told you now because I know some of you are already doing some Lyapunov exponent RIE diagrams, right? So this is just an idea. Okay. So this is correctness of your bifurcation diagram. If a bifurcation is happening, but your Lyapunov exponent is not touching 0, then you know the Lyapunov exponent is not correct. Okay. So this is a way of correctness of your bifurcation diagram. Now let us come to your assignment. assignment 2, okay? This is your assignment. This is your assignment, okay? The assignment is consider not a 1D map, rather a 3D map. This is the 3D map, okay? You can see X, Y, Z, right? Now your task is on the AC plane. So A, B, C, D are parameters. A, B, C, D are parameters. Your task is on the AC plane. I have drawn this coding part, a bifurcation diagram, where the blue part, mathematically, I ran a 2D code for loops, and I found this is the region of stable fixed points. Okay. Now, when they go to unstable fixed points, you see the instability is reached. So white is unstable, blue is stable. White is unstable, blue is stable, right? So this curve represents the pitchfork bifurcation. Okay, this curve, the red curve is known as the pitchfork bifurcation. Your job is to prove that it is indeed a pitchfork bifurcation. It is indeed a pitchfork bifurcation. Okay, why it is a pitchfork bifurcation? Okay, that much, nothing else. First, of course, you have to do coding to know whether it is coming correct or not. So you don't worry about the blue part. You just have to draw the AC plane and just have to get this line. Numerically, that is one part in Python. Second part is theoretical. So you have to prove that indeed this is a pitchfork bifurcation by the facts I told you. So you have to do two things. One is theoretical, another is Python. Okay. Agree? Fine. So the assignment, when it will be due? It won't be next Friday, right?